All right, let's talk about nuclear fusion. Right now, there is so much buzz around it. You hear about these game-changing breakthroughs all the time. So today, we're going to cut right through all that noise. We're going to separate the real, genuine scientific leaps from the media hype to figure out what's really going on in this quest for basically limitless clean energy. And this, right here, this is the dream. This is the incredible promise of fusion energy. It's why we are trying to literally replicate the power of the sun right here on Earth. For decades, this has been the absolute holy grail, and it's driven a massive global scientific effort. So how are we going to break this all down? Well, first we'll get into that incredible promise. Then we'll dig into the genuine scientific leaps that have everybody so excited. We'll look at how that's kicking off a whole new private race for fusion before, grounding ourselves in the tough engineering reality of it all. And finally, we'll look at the long road ahead and figure out what it all means. So, first things first, let's just set the stage. Why is fusion such a big deal? I mean, why are we pouring billions upon billions of dollars and decades of research into this one single goal? Well, the answer is all about how it's fundamentally different from the nuclear power we already use today. Okay, so this is the crucial difference. Fission, that's what powers our current nuclear plants, it works by splitting heavy, unstable atoms apart. And it works, for sure, but it creates that long-term radioactive waste we have to deal with, and it carries inherent risks. Fusion is the complete opposite. It takes light atoms like forms of hydrogen and smashes them together. This releases a tremendous amount of energy with no long-lived nasty waste. And there's just no possibility of a runaway chain reaction. It's fundamentally safer. So with that incredible promise in mind, let's get to what's driving all the recent excitement, because there have been some genuinely historic achievements lately. We're going to look at the two main ways scientists are trying to, bottle a star and the huge progress they've just made. And these are the two leading approaches. On one side, you've got magnetic confinement. You can think of this like building an invisible magnetic bottle to squeeze and heat this stuff called plasma inside a donut-shaped machine called a tokamak. On the other side, you have inertial confinement, which is way more like a microscopic, controlled explosion, using these giant, powerful lasers to vaporize a tiny little fuel pellet. And these aren't just ideas on a whiteboard. I mean, look at this. On the left, you can see the unbelievable scale of the laser bays at the National Ignition Facility in California. That's the laser approach in action. And on the right, that's a diagram showing the complex magnetic cage inside a tokamak, the kind of machine driving that magnetic approach. Now, the first absolutely monumental breakthrough came from the laser camp. In late 2022, the National Ignition Facility, or NIF, did something that had never been done before. For the very first time, they focused all their lasers on one of those little fuel pellets and got more energy out of the fusion reaction than the laser energy they put in. This is the holy grail milestone called ignition, and it was a genuine world first. So what about this number? 1.1 megajoules. To put that in perspective, it's about enough energy to boil a few kettles of water, so, we're not powering a city with that. But that's not the point. What it proved was something absolutely fundamental. The basic physics works. It is scientifically possible to get more energy out than you put in, and net energy gain is possible. Then, just recently, the other team, the magnetic confinement folks, had their own landmark moment. At the East facility in China, which they often call an artificial sun, researchers absolutely smashed a long-standing barrier for how these tokamak machines can perform. They managed to operate their machine way beyond what's known as the Greenwald density limit. Now, you can think of this as kind of an old speed limit for tokamaks. For years, the thinking was if you try to pack too much fuel, too much plasma into that magnetic bottle, it just becomes unstable and the whole reaction fizzles out. Well, the East experiment found a way to run in a much higher density mode, which is a really critical step towards getting that net energy gain from a tokamak. Now, these incredible scientific leaps, they didn't just happen in a vacuum. They lit an absolute fire under the private sector. We're now seeing this flood of venture capital money and a new, really aggressive race, with startups promising to put fusion on the grid in the next decade or so. And this is a fantastic snapshot of the key players in that race. You've got Helion, which is betting on a totally new way to get electricity directly out of the machine. Then there's CFS, an MIT spinout using powerful new magnets to shrink down that classic tokamak design. Tokamak Energy is doing something similar but with a more spherical apple core shape. And TAE Technologies is going after a super clean but technically way harder fuel. Everyone's taking a slightly different shot on goal, which is exactly what you want to see. But, and this is a really big but, this is where we have to take a pause. The private money and the bold promises are super exciting, But we need to ground ourselves in the reality of the immense engineering task that is still ahead. This is where the hype runs smack into some very, very hard physics and material science. And honestly, nothing illustrates this better than the timeline for ITER. This is the massive international public fusion project being built in France. Back in 2016, the big goal was first plasma by 2025. Well, now, after facing just huge first-of-a-kind challenges, the new target for just initial operations is 2035. It just shows the massive gap between a plan on paper and the tough reality of building these things. This quote, which you see in online discussions about fusion startups, it just perfectly captures the mood. Hofstadter's law is basically the old saying that any complex project will always take longer than you think, even when you know it's going to take longer than you think. It's that healthy dose of skepticism that really applies here. And this slide right here gets to the absolute heart of the remaining challenges, and they are huge. First, that net energy gain at NIF is not the same as putting electricity on the grid, not even close. The entire facility used hundreds of times more energy from the grid to power up those lasers than it got out of the reaction. Second, we have a fuel problem. One of the main ingredients, tritium, isn't something you can just dig up. We have to figure out how to breed it inside the reactor itself, a technology that's still pretty much unproven at a large scale. And finally, we literally have to invent materials that can survive for years right next to a star, withstanding insane heat and radiation. These aren't small details. They are the core engineering problems that have to be solved. So if we're not getting commercial power plants tomorrow, what are the real signs of progress we should be watching for? What are the actual milestones that will tell us we are genuinely getting closer to the finish line? Here's a little checklist for you. Step 1, we need to see these new private machines actually get turned on and create their first stable plasma. Then comes the really big one, net system gain. That's when a whole power plant facility puts more electricity onto the grid than it pulls from the grid to run itself. After that, it's all about durability, proving the parts can last, and showing that self-sustaining fuel cycle actually works. These are the real engineering goalposts. Okay, so let's try to pull all this together. We've seen the incredible promise, the genuine breakthroughs, the private sector hype, and the pretty sobering reality. So what does this all mean for our energy future? So here it is, the bottom line. Yes, the progress is absolutely real, it's historic, and the science is moving faster than ever. No, this does not mean commercial fusion power plants are just around the corner, ready to power your home in a few years. But, and this is a big but, for the first time ever, the idea of a pilot plant actually connecting to the grid within the next 1 to 2 decades has moved out of the realm of science fiction and firmly into the world of engineering possibility. And that really brings us to our final question. We've come an incredibly long way, and that goal of fusion energy feels tantalizingly closer than it has ever been before. But as we watch for these next critical milestones, we're all left to wonder, is this final difficult stretch to the finish line going to be a sprint, or is it just the start of another long marathon?